Now, aside from Newton's second law, there are many other organizing principles in engineering that are important, and the most important of these are your basic conservation laws. These are very powerful and form the basis for a variety of mathematical models. They're powerful because they are conceptually easy to understand. Conservation laws describe how the change of the system state is equal to whatever comes in plus some production term minus whatever comes out. So I've drawn that up here, and we can say that the delta, or the change in the system state, is equal to whatever comes in, phi of n, plus the production term, minus whatever goes out. So that is what is causing the change in the system state. Now, if our production is 0, let's just change the pen. If our production is 0, we have a steady, well, we simply say that the change of the state of the system is the difference between what comes in minus what goes out. Think about what you've just done with Newton's second law and our falling parcel. Essentially, it's the same thing. That is, the change in velocity, so the derivative of velocity with respect to time, the acceleration, is equal to the force driving the acceleration, which we said was the difference between the downward gravitational force and the upward drag force. So if we drew that, we would say that it's the change in the velocity is the difference between our gravitational force and our drag force. Now, if delta equals 0, we have a steady state computation, and you've already seen this in applications in fluid dynamics. That is, the flow Qn equals the flow going out. We can apply this to a pipe network problem. For example, if we had a flow rate of 100 coming in to our system, and we had 80 coming from, let's just say 80 liters per second, so that's 100 liters per second, and 80 liters per second coming in from the top. And if we have 120 liters per second going out at the bottom, we know that the flow coming out on the right here must equal to 60 liters per second. In other words, whatever comes in must go out. You can apply the same thing to work out the terminal velocity of an object. In other words, your resultant force, if your resultant force equals 0, you're at terminal velocity. So therefore, the body force due to gravity is just equal to drag. So that we can write as the gravity is equal to drag. Now, we've assumed a linear relationship between drag and velocity, and this is not always the case, but we'll keep it simple for now. So what I mean by this is that the velocity is really just equal to mg over our drag coefficient c. Now, don't be fooled by the simplicity of these two examples that I've just shown you, because these two examples embody the fundamental ways that conservation laws are employed in engineering. And we're going to see that in our next example.